Welcome everybody, and thank you for joining us today. We'll have a discussion today around deploying DWDM and for both the core network and for wholesale services. Want to start off just by giving you a little bit background on Tejas Networks. Tejas Networks is headquartered in Bangalore, and we have headquarters in the Americas, both in Dallas and in Mexico City. And we have over 500,000 network elements deployed globally, including very large DWDM networks spanning entire countries. In the Americas, we have about 12,000 network elements deployed. We're a very R&D software-focused company with software-defined hardware, and we create a very flexible architecture for the future. And to reinforce that concept, I'll walk you through how we do that today. So the webinar today will go through three main topic areas. One, just overview of where the wholesale service market is going and where interface requirements, bandwidth, distances, etc. Opportunities for deployments, right? And the next gen products that Tejas Networks can bring to solve those deployment issues. So first, let's just start a look at the applications driving global wholesale markets. Of course, mobile broadband is huge right now, and with the advent of 5G, everybody's looking at how they can scale their network a little bit better, a little easier in both the access and core, and then for wholesale backhaul of wireless services, that was very prominent 4G, and will probably be even more prominent in 5G in terms of volume and number of sites. Also, cloud and internet data centers. Right now, they're extremely centralized, but we see that moving out farther and farther from the centralized locations to smaller data centers at not quite the edge of the network, but about the aggregation layer of the network. And that's to reduce latency for a number of applications. Everything from 5G, right? Getting data there faster, in the enhancements in video, etc. Home broadband is taken off during the COVID situation, right? And will probably continue to grow significantly, and we'll look at some of those numbers. And the Internet of Things is just starting to ramp up really, especially being forced to the forefront because of COVID. Right? So COVID has accelerated the bandwidth demand, of course, for all of this. As you can see in this graph, in 2019, we had about 1.7 zettabytes per year. And we're expecting from Otn, they say there's going to be about 244% growth up to 5.7 zettabytes. Now, to give you a little indication of what that is, I just want, sometimes we get lost in these numbers because it's so easy to say ZB and move on. But I wanted to give you the size of the number of zeros that we're talking about. So there's about 7.5 billion people on Earth, right? And that's, you've got 7.5 to 10 to the 9th, right? The distance to the nearest galaxy from us is about 1.46 to 10 to the 16th miles, right? But a zettabyte is 10 to the 21st. So that's 5.7 followed by 20 zeros of data. And that's a lot per year, and growth, even a small amount of percentage growth, right, would result in an extremely large increase in the amount of bytes per year within the network. And this is global, of course, right? And it may be even underestimated considering what's going on with COVID. So Otn predicted in January this year, before COVID situation started, this blue line of growth pattern. Right? And in August, they came back to it and reevaluated it. And they gave three variation forecasts based upon COVID lockdowns. One with 3 months of restrictions, this is the purple line. One with 6 months of restriction, and one with 12 months of restriction. Now the variation in that is about 15% for 2020. So although they see it rejoining back up at about 3.5 zettabytes per year. You can see right now in 2020, they believe that we're about 15% above their estimations from January. So in 9 months, right, they think we're about 15% above. I personally don't think it's going to, back off. I think I've been in this industry a long time, and I've never seen it, slow down at the rate they're expecting for 21 and 22, the growth to slow down as much as they are here. So I expect to see the growth continue. So if that's a 15% increase, that's another zettabyte. And just to give you an indication of that, my house, right, it's not it's a fairly common one. I live in Massachusetts, right? We have 4 people in the house. We have a home office, a university student who can't go to university, a grade 8 student who's work from home, all of our videos over the top, plenty of medium bandwidth gaming. So that all comes into play. But if you look at these charts for a second, last month in my home, right, we're under 44 gig a day. Right? This month, with university coming back into play and with my daughter studying from home for school, right, bandwidth in my house is up 30%. And that's a significant jump. Now that might drop back down this year. Hopefully we get some people back to school, but it's rare to see it go up and down. It usually just goes up. So in general, my house does about 1.3 terabits of data per month, terabytes of data per month, right? Or 14 terabytes of data per year. Now, we're not a large house. Yes, it's over top of video, but it's not that strange these days. Having students in the house, yep, but 14 terabytes of data, that's a lot. Right, and with the number of households around the world and the continuing growth of bandwidth consumption, there will be a large demand on the wireless networks, on the broadband networks, on enterprise networks for exchange of data that goes through the internet. Right, and we expect to see significant changes that stick around with us through 2021 and 2022. So we're looking at networks that can address the post-COVID requirements. The ability to rapidly evolve, upgrade bandwidth, change bandwidth, right? Reconfigure themselves from a network perspective relatively easy without going out and moving patch cords. The ability to transform the network into delivering superior SLAs. People working from home more would mean, I got to have that bandwidth all the time. I can't, be out for 3 hours. I don't want to be held back from my work or my Zoom meeting simply because my daughter's got to do something for schoolwork. And this ability to seamlessly scale bandwidth from the access to the edge to the core. And we'll be looking at a number of those capabilities to scale that bandwidth relatively quickly and easily. So what do we see in the service characteristics of wholesale and core services? I'm kind of lumping those together. They're separate, but if we just do every one individually, it'll take a significant amount of time. So in the interest of moving forward here, we're seeing that, packet services in general are any range from, up to 20 gig these days in North America. Right? Virtual circuits up to 20 gig. Now, I understand that there's, significant variations in that, and the bulk of it is, below 100 meg, but there's still a, growth pattern that says we're looking at packet services up to 20 gig. We'll cover 99% of them. And then we're looking for what can we do with OTN circuits. So at that first layer 1 TDM layer, what's the, the general grooming level? It's 10 gig E for the most part these days, but 100 gig E is at grooming at 100 gig E will become more and more important as well. But the wavelengths themselves are moving well beyond that. 100 gig is fairly common these days in the core, in the long haul core, and in most of the metro, but it's moving farther and farther out towards the edge as well, and in the smaller and smaller metros. And all of these require a scalability and availability that is, been common in telecom, but not common with all of these circuit types at this size, right? Quality of service that's guaranteed right from the wavelength level right up to the packet services level, and the ability to provide security, provisioning, and service management. There's a number of ways to do all of this. We'll just address the Otn and Dwdm one today. When it comes to the growth of opportunities, there's a couple things that research has given us to work with. Right? The first one here on the left-hand side is related to the number of ports sold per year. Right? And this top line is 10 gig ports. And you can see it's been starting in its decline for a few years now as 100 gig came online. And they expect it to continue to decline. This is new ports per year. There's still a large installed base of 10 gig and interfaces, and that will not go away. But for the growth pattern, the number of new 10 gig ports, as it moves away from being on both sides, as in 10 gig on the client side and 10 gig DWDM, right? That'll half the number of ports because we're moving to 100 gig. And then the red line here is 100 gig ports, and it's been steadily climbing, right? It took a big burst when it first started to be deployed in the long haul, and now it's just steadily increasing. Right? 200 gig, the belief is that 200 gig is pretty much capped out, right? From a number of ports growth. There'll still be a large amount of deployments year over year as 200 gig is still an extremely viable technology for backhaul. It's very cost effective, and being able to take a number of 10 gigs or 100 gigs into a 200 gig. But perhaps the most interesting is the large push on 400 gig interfaces, especially 400 gig E. And being able to address that is important for all of service providers, whether it's data center interconnect capabilities or backhauling from a remote POP to a data center itself, right? There are a large number of opportunities for that. And enterprises moving to 400 gig E will take some time, but 2024 is not that far away. And I think that'll be allow us to reach this curve quite easily. If we look at where the global data center interconnect forecast is split by revenue per year for equipment, this isn't all, but it's revenue per year. And if we look at the long haul piece, it remains relatively flat. And while submarine will pick up, we're looking at most of the revenue for data center interconnect coming within the metro, right? Between data centers in the metro, distances under 600 kilometers for a ring, interconnect at 100 kilometers or 200 kilometers between sites, maximum. And most of that, I believe, will be even closer, like 30 kilometers to 60 kilometers apart, as you get smaller data centers closer to the edge, offloading the computation requirements and storage requirements that are currently done from more centralized locations. Okay. So let's look at some generalized forces that apply for this new optical layer. So we've looked at, okay, there's bandwidth growth, right? But what does that mean for my network structure? Like, how do I really address that? Now, this is going to be generalized, so there's a lot of variables in play here. We don't have time today to go through all of them, but I want to make sure we get through some of the general concepts. And I'll walk through this a little bit more as we go along. So the first part is you're selling a signal rate, right? So the signal rate of all 100 plus 200, 300, 400, 500, 600 gigs transport is based on a formula that basically says I've got two poles for the light to go through. So I've got an X and a Y pole of light. And these are polarized light streams, so I can take whatever I'm doing with the light and have double that amount of bandwidth on it, any single wavelength. Not on fiber, on any single wavelength. The second term here is bits per symbol. So now we're into the point of varying the number of bits you can get out of every time period of light. With 10 gig, it was pretty simple. You got, you know, you got 10 gig of data. That's it. Like there wasn't any variation on that except, okay, we could go 9.9 or up to, almost 11 gig, but it wasn't very much variation in there. Now we're going to get into, instead of just 1 bit per symbol that we had in 10 gig, we're getting into 2, 3, 3.5, 4, 4.5, and on. And we can vary that number of bits per symbol, right? And then we have the symbol rate in gigabaud. So that's the number of, symbols that we can see, the baud rate, for any period of time. And we can vary that as well. So these 3 terms give you your signal rate. When that relates to your service offerings, though, your service bandwidth offerings are based upon the distance you have to go and the spectrum usage that you can allocate to that service. And the distance is directly relatable to the bits per symbol. You increase the number of bits per symbol and you have a shorter reach. That's glossing over some, details in there, but this is the generalization. The other generalization is if you increase the symbol rate, you increase the spectrum usage. So within a fiber, right, if you increase the symbol rate, you increase the spectrum usage. The service price offering, so the price you would charge for that is based upon the cost per modulated bit. So I can get multiple bits per symbol now. So I look at the cost per modulated bit and the efficiency that I'm using, not only my fiber, but the wavelength itself and the number of wavelengths that I have across my entire grid. So again, this is generalizations, but it helps you just give you a understanding of what we're doing with this latest technology. So coherent transmission, which all of these are based upon, is the all the 100 plus symbol rates are based upon, is paramount to this new technologies. And I'll give you a little bit of an overview of this. So in the transmitter side, we have a laser. And we split and polarize that light into 2. So one would be this x-axis that goes up and down, and one would be the y-axis that goes side to side. On each one of these, we modulate a signal into it. And we modulate 2 signals into it based upon phase, and then so that we get 4 coordinates on each signal that's going through. And then we do the same on the other for the y-axis. And then we bring them back together and send them all in the same frequency of light down the fiber. So now we can do multiple frequencies up to 80 channels, etc., of light, and have 2 basic signal patterns, right? We have the X and the Y. And we're changing the way that we look at these signals. Instead of it being on-off keying, we actually, in phase shift keying, we change the waveform. Instead of continuing it, we shift the phase when it transitions from 0 to 1. So now we removed a lot of the dispersion problems because we're not worried about that signal spreading out and reading it wrong. We're just looking at the phase shift. Okay. And then we also look at variations in the amplitude for QAM. So if you look over here at the number of symbols, right, the different patterns that we have for coherent transmission, DPQPSK, dual pole, 8 QAM, 32 QAM, 64 QAM. You'll notice there's a lot of data that can be pulled out of this. And the more you put into it, right, the more data you put into it and the more amplitude modulation you put into it, right, the greater the number of bits you can pull out. So we have, in QPSK, we have 2 bits per symbol. In 8 QAM, we get 3 bits per symbol, right? In 16 QAM, we get 4 bits per symbol. In 32 QAM, we get 5 bits per symbol. And at 64 QAM, we get 6 bits per signal. But just like you would have a hard time seeing every individual dot here at a distance, the receiver will have a hard time seeing every individual dot at a distance, especially as that light travels farther and farther through the fiber. So the QPSK has the longest reach capabilities, and as we move towards the different QAM interfaces, we have to do more and more signal processing to make sure that we can receive that signal. Right? So again, here's the formula that I showed in the previous chart, and that's the basis of the transmitter. If we look at the receiver side, we have a input signal that was created above. The local oscillator then tunes that input signal to the particular wavelength that we're looking at. So if this was set on wavelength X, this local oscillator is tuned to wavelength X. Then we demodulate it, right? These are the photodetectors to be able to turn it from, and then to turn it into analog, and then analog to digital. And then we get into the real heart of these technologies, these higher bit rates, which is the DSP. Now the DSP does a lot of things that we need to do just from a generalization to get the performance out of the system, like PMD compensation, dispersion management, nonlinear compensation. It also does a formatting on the pulse itself to make it a little easier to see, and provides next generation effects up to 12, 13 dB to be able to correct errors as they receive. So these two areas basically become the glasses, right, that for each of these signals. So if you want to see the 64 QAM, you have to do a lot more DSP functionality. And then your phase recovery as well is an important feature of the DSP. Right? So all of these functions join together, and all of them have their individual costs, but it's not a linear cost. Right? So it's not you go from 2 bits to 3 bits to 4 bits. 2 bits is not half the price of 4 bits, but there is a relationship between them. So we're going to get a little bit into how do we best utilize all the capabilities that we have, right? And one of those capabilities is to vary the baud rate. And you're thinking, okay, well, that's part of the formula. So I've got 2 poles, and I get the number of bits per symbol that I just reviewed. Now let's look at the baud rate. So if we're doing 100 gig or 200 gig signals, there are basically 3 choices that we can use right now, and someone might come up in the future. We can run at 31 gigabaud, 34 gigabaud, or 42 gigabaud. Now, if we're running at 31 gigabaud, right, the size of the wavelength, right, is in the shape of the wavelength is like this. So it occupies this much spectrum. If we run at 34 gigabaud, the amount of spectrum we use increases. And if we run at 42 gigabaud, then it increases even further. And these are fixed. So a standard 100, 200 gig without variable baud rate capabilities would have wave formats that look like this and occupy this much spectrum. Now we're moving into variable gigabaud. So we can tune from 27 gigabaud to 70 gigabaud and get bit rates from 100 gig to 600 gig. Now, I want you to watch that again as we introduce it. As the baud rate goes up, yes, the size of the the amount of spectrum used increases. Right? So how do we maximize that spectrum usage? Well, if you have a network and you have a number of wavelengths that go over it at fixed rates, right? You're going to sometimes have holes in between them of varying sizes. So how do you fit in an area where you have 45 gigahertz available here and 62 gigahertz available here? And how much bit rate can I get? Well, that's functions, as I've told before, on that formula. It's a function of, you know, the distance you want to go and, you know, how much spectrum you have to use. So we can take a 45 gig channel from a variable baud rate transceiver, right, and fit it into the space that we see down here on the left. Or we can take a 62.5 gigahertz channel. Depending on the distance you want to go and the baud rate, the bit rate that you want to get, you would choose one or the other depending on the spectrum that you have available. And this gives you a lot of flexibility in using the maximum bit rate possible for the distances you want to go, right? And provide the best efficiency on your network. Now, a network that's aware of the baud rate and the modulation selection, right, is capable of saying, okay, I want to go X number of distance through X number of ROADMs. What's the best baud rate I can get? So we're going to use an example here of 200 gig. If I want to go at 200 gig and I have a 8 QAM that occupies 42 gigabaud, right? That's my slicing. That's how I, you know, encode the signal. Right? I can make a reach of about 1,400 kilometers maximum. Right? And the OSNR penalty path looks like this. If I want to do 200 gig at 4 bits per symbol using 16 QAM, right? Well, the amount of spectrum I'm using is going down in this particular case, right? And I am on this path, but I can only reach 800 kilometers. And that's because I'm looking at more symbols, more points of light, double the number of points of light in 16 QAM. So it gets, the chances of there being an error or a problem increase. So I have to have a better, you know, signal. At about 800 kilometers, the signal just degrades to the point that FEC can't recover it. But if I use a combination of 8 QAM, and this was mistyped here, so it's 8 QAM and 16 QAM, I can get 3.5 bits per symbol, only use 36 gigabaud, get my 200 gig, and get a reach that's in between the two of these, right? But the reach is actually a little bit better at 1,600 kilometers. Now, you don't have to remember all of this by any stretch of the imagination, because there's tools available from Tejas, et cetera, that can take you through this. But here's the great thing about it from doing wholesale services. You're able to construct your network how you need it, right? So when you get into this concept of utilizing the spectrum that you have available the best way possible, then we need a variable bit rate requires a flexible Dwdm grid. And why would that occur? Well, if we have a fixed grid for the network, then we have fixed spacing for each wavelength to go down and be safe. Makes sense? You stick to your lane and everybody's fine, right? But if you have a variable bit rate capability, then you can vary the width, right, of your signal, or the amount of spectrum that's utilized, and you need a flex grid capability. So if you try to put these larger signals at higher bit rates into this fixed pattern, they don't mix very well. They're off, right? They're not in the grid very well, so the ROADMs won't work, etc. But with a flex grid, you're able to define the spectral use of each channel as required. So for the larger signals, the ones that use more spectrum, I can allocate more spectrum to them. And for the smaller ones, I can allocate less spectrum. Right? And it's part of an automated system within the network. Right? You don't have to like go around and pre-tune all these, et cetera. But it's a capability that allows you the maximum density on your fiber. So you're increasing your fiber capacity. You're using the spectral efficiency the best. You get these great big super channels, as they call them, right? And you get a QoS that's in line with your service. So efficiency goes up significantly. And for wholesale systems, you say, okay, I want to use that fiber as much as I can. I got some customers at 100 gig, some at 200 gig, some at 400 gig E, right? And we've seen the demand for that is going to be increasing. So with a flex grid, you're able to do not only put those signals onto the fiber, but you're able to also say, okay, if I'm running 400 gig and I need more bit rate capabilities on it, and I want to go a longer distance, I can mix and match, right? 4 bits per signal, or 4.5 bits, or 5 bits, etc., and get the distance I need out of the network and out of that service. So Tejas Networks brings you the platforms that allow you to bring this capability to your network. We have a 2U chassis, we have a 4U chassis, right? And we have a 9U chassis. And these chassis take the cards that we're going to be talking about here in a minute and allow you to run it over, single fiber. We do have a single fiber 100 gig solution, right? So you can do 100 gig and only use one fiber out of your network, especially valuable for access or when you're leasing fibers from other companies. Run it over dark fiber, lease wavelength, third-party optical line system. Our alien wavelength capability to run over top of somebody else's line system is proven throughout the world, right? And then we have our own Tejas optical line system. So I'm going to concentrate primarily around the next generation of services that you would be able to deliver. That would be done, in our case, through a couple of line cards. Right? On the right-hand side, you have 2 ports here. These ports can run from 100 gig up to 600 gig DWDM on the line side, and they're tunable. And they're not tunable in like, okay, I can do 100 gig or 200 gig or 400 gig or 600 gig. We can also tune it to run at 350. So if you've got a distance that 400 gig doesn't work at, but 350 would, and remember the formula says we can vary this, so I can get that 350 gig, right, and not have to drop right back to 200 gig. So we have variable bit rate capabilities throughout our system. So this particular module has 12 QSFP DDs, right? And the 12 of them can be used in this manner. I can use all 12 of them for 100 gig interfaces. So in one card, I get 1.2 terabits of traffic. And that can do a lot for your wholesale environment and for your core network. You can run your core network and your wholesale over this and have the 600 gig wavelengths coming out. Now these 600 gig wavelengths, right, like I said, they're fully DWDM capable. Okay. But if you have a customer that says, or a requirement within your own network to run at 400 gig E, then you can plug one 400 gig E interface into a slot, and the other 3 slots are turned down, so I can run at 400 gig. Now, I can run 3 ports at 400 gig. So that makes 1.2 terabits. That's over 2 600 gig lines. So of course, we're splitting one of the 400 gigs into 200 gig going on one port and 200 gig going on the other port. But you can still get 1.2 terabits of capacity. If you're looking at a situation where you're doing more 10 gig services, right? But you still want to be able to do all of the other services I talk about, then we have a card that has 40 SFP pluses. So you can mix and match 10 gigs, 100 gigs, and 400 gig interfaces. All the requirements that we've seen is the direction for large enterprises and for ports delivered within the network on the chart back a few, on that graph a few charts back. You can deliver all of those off of one particular card. Again, 2 600 gig outputs, right? But in this case, we've opened up 40 SFP pluses. Now they can run 10 gig E, of course, but they'll also be able to run any of your existing OC192 or STM64s, OTU2Es, of course, and fiber channel. So this card can do a lot for not only your network, but for customers' networks, transparent carriage, wholesale backup, etc. So enterprise services can be delivered off this as well. And this card can be run in 1+1 mode, protected services, and other capabilities for the protection as well. So what did that bring you, right? You have two cards that are able to do from 100 gig to 600 gig on the transmission rate, optimized to make sure that it's viable for you from a dollar perspective. Continuously tunable baud rate, so you can change that as required, right? And that means you can say, I can tune it up or down depending on what my customers required. I can interleave modulation, as described before, so I can have modulations of one rate or another rate, right? And that modulation techniques and shaping techniques gets that 3.5 bits per symbol that, you know, we talked about that looked a little strange, but the advanced modulation capabilities will allow that. We give you the capability to hit all of those interfaces that are going to be in high demand, get you super channels, right, and even encryption capabilities, right? All of which may be required for not only data center interconnect, but for 5G requirements as well. And the evolution we can bring to the optical layer, not only through our amplifiers, but you know, we have also auto equalization and performance balancing, optical performance monitoring capabilities we can bring to you as well. ROADMs on a blade that integrate all of this functionality into a single card, and OTDR functionality. Now those capabilities will allow you to deploy a network quicker, deploy a wavelength quicker, and at a lower operational cost. Right? Especially, you know, the functionalities around auto balancing, right? And optical performance measuring. The OTDR is great for operational perspectives. You can, you know, know where your fiber cut is and dispatch quicker. In addition to these hardware capabilities that integrate software, we have also WSON. And WSON is the ability to software provision wavelengths across the network. And that is extremely important as we look at this dynamic infrastructure that we'll be evolving into, you know, over the next 3 to 5 years. And it started now. I mean, it's not like it's 2 years away or 3 years away. It started now. It's just rolling out to more and more locations and more requirements from wholesale, from customers who want wholesale capability. So those wholesale providers that we're targeting out are mobile operators, carriers, and enterprises. I'm sure that you've seen all of this before, and you know, whether or not you're carrying traffic for another carrier or for a mobile operator or for a large-scale enterprise or even a medium-scale enterprise now. Right? So the structure that we can bring with it is not only the mux bonding capability up to higher bit rates, but also an OTN switching capability as well with secure transport. So we can look at situations where you're just doing 100 gig, right? Just 100 gig, but 100 gig to a core node. You're doing bulk encrypted services from an edge data center into the core, right? And you're aggregating another customer here from 100 gig, and you can bring it all back and send 400 gig to you know, to POP A or web scale company A, and 600 gig to another one. All of this is capable, right, with the technology that I've just shown you, right, and with the other cards that we have in play. And this is an extremely dynamic capability. So you can tune this up to from 100 gig to 200 gig to 600 gig on the cards before, or you can go in lower at a more fixed 100 gig to start with and then upgrade to 200 gig. Or you can have something that does 100 gig and 200 gig if that's what you're looking at for expansion to that particular edge data center. The other way we look at this is how do we make it bring OTN into the transport network to make it more cost effective to deliver services. In this case, we have an enterprise, right, set that is A and B, right, and then probably another one over here that's over top of a service provider's routed infrastructure, right, and back to a core node. It's typical to look at doing, from these routers, doing 10 gig interfaces and either turning up Dwdm on the router, which is kind of okay, but operationally it's a little bit blind, or turning up additional fibers. So how do we like lessen the cost of this network structure? So we can reduce the number of fibers that are used, and we can also simplify the design for these routers that would collect from the customer sites. And we can do this by introducing an OTN switch in our micro OTN device, which is called the TJ1600 2-slot. And in this case, we bring in the router capability directly into our mux bonding cards, and we mux this up to 100 gig. Now, the cost will go down, your performance will go up, and your flexibility to turn up new services goes up at the same time. So you'll have 100 gig going from each of these nodes in both directions to create any ring capabilities that you want, and you take from the router and you can go to enterprise A or enterprise B or back to the core, whatever is required. We accomplish this by taking the mux bonder cards and putting 2 in a shelf and creating a 400 gig cross connect. So we can groom at the 10 gig levels. So this particular router could actually have 3 ports on it and have one of them go back to the core, one of them go to this particular enterprise A, and one of them go to enterprise B. So we have add drop functionality on a 2U device at 100 gig bandwidth. Now that could be 100 gig DWDM, it could be 100 gig LR optics if these are close together, or ER optics. But you're running at a much higher bit rate for a lower cost, and it's easier operationally. You also save fiber. Right? And all of this can be done with the devices that we're talking about here. And this is the micro Otn architecture. It's a 2U chassis, right? It will support the cards up to 600 gig, but the ones that we're talking about right now are 10 gigs into 100 gig. And we can do single fiber operations as well. So use a single fiber around the ring, not 2 fibers, one for transmit and receive, but a single fiber with wavelengths going in one direction and wavelengths going in the other direction at a DWDM spectrum range. Another great technology that we bring to the forefront here is our legacy DWDM. We can look at the legacy DWDM that you have installed and upgrade that to 100 gig or 200 gig, plugging into the existing network structures. No replacement of the existing network. We plug in our devices and go. And think about the cost savings on that one. I don't have to operationally go out to intermediate sites. I don't have to buy new ROADMs or new ILAs. I can just plug in a higher bandwidth and go. And we've proven this over many networks, one of which is this one that I've displayed here. This is 820 kilometers network, point-to-point span, right? 57 channels were already lit, and we dropped in 100 gig alien wavelength on it from end to end through all the ROADMs here. All the ROADMs, all the ILAs, without touching the existing infrastructure. Our single fiber capability can give you the ability to optimize your fiber, right? So you have 100 gig on one fiber in both directions, up to 106 kilometers. Or if using 2 fibers or 2 wavelengths to get 200 gig, up to 101 kilometers. So one fiber at 200 gig total bandwidth, right, is capable on a single fiber. Now this has been done with 10 gig before, but it's not done with 100 gig. So we can bring that technology to you for your wholesale environments or for your core infrastructure. And all of these are managed through a single network management system that gives you a graphical interface with usage capabilities right down to the ROADM level, right? So you can see from end to end. But where do you go next? So, well, how do we scale this up next? And the way we're looking at scaling this is we've launched the TJ1600 S and I. The S part is the switch part. and the I part is this I/O shelf. So from a modular platform, we can scale up to 48 terabits. So we can bring in wavelengths at 100 gig, 200 gig, 400, 600 gig, all those services, and switch them at a layer 1 capability, right, and send them in different directions, up to 48 terabits on a single device. Each one of these I/O chassis is capable of doing a 800 gig of OTN, right? And we can scale this by not only adding additional switch fabrics, but additional I/O modules. And we can see this on this side. So we have a scaling from a 1 rack unit up to 35 rack units, right, with the current technology, and we'll go beyond that, right, still remaining within 35 rack units to go up to 48 terabits. And this can give you the extreme advantage of not being limited by the scale of a conventional shelf. So we have a great OTN switch up to a terabit, works great, but scaling beyond that, you want something that's extremely flexible and is driven by the cost or the revenue of the network, I should say. So the cost is proportional to the revenue. So you don't want to put in a great big backplane, and you don't want to have to like throw a whole bunch of cards at it day one, right? And a backplane that can handle every possible option. We give you the I/O capabilities that scale in those 1 rack unit shelves, and a switch fabric that scales. So yes, you have a larger chassis, right? But its only function is to not do I/O, but just do switching. Right? So you're not limited by the number of faceplate ports, etc. You need more ports on the faceplate, you add another 1U shelf. And that capability will allow us to have a access to core portfolio, because that goes from ultra-converged broadband right through to a 48 terabit systems, delivering on not only the wholesale services that we talked about today, not only the core network services we talked about today, at rates up to 600 gig, but also all your edge and access requirements. So the key takeaways are the growth of data is significant, right? I don't think it's going to back down. The evolution from 100 gig to 600 gig is in front of us, and we're capable of delivering on that. Right? And encryption is there with it for the security aspects. So with that, I know I went over time, but I appreciate all of your effort